Welcome to qnawire.
So for this problem, the first thing to note is that the force acting on the collar due to the spring is equal to the force constant of the spring, K, into R minus the position of A, RA. Now for part A, we have that the theta component of the force is equal to 0. And at A, the radial component of the force, so this force always only has a radial component, but at A, this radial component is minus F due to the spring, and this force is equal to 0 as the collar is held constant. So if the resultant force on the spring is 0, we have that the acceleration in either component is both 0. So the radial component of the acceleration of the collar at A is 0, and the theta component of the acceleration of the collar is also 0. So there is no acceleration of the collar at this point. So that's our first answer, our answer for part A. For part B, we'll use the fact that the sum of the radial component of all the forces must equal to MAR, where AR is the radial component of the acceleration. So what this means is that the force due to the spring is equal to M times R double dot, so this is A, minus R theta dot squared. So M into d2R dt squared minus R d theta dt squared. And we note that the acceleration of the collar relative to the rod is simply d2r dt squared, the second derivative of the position or the first derivative of the acceleration. And so at A, we have that 0 is equal to m into the acceleration of the collar relative to the rod minus r theta dot squared, which is 150 millimeters times 16 radians per second squared. And hence we get the acceleration of the collar relative to the rod is equal to 38,400 millimeters per square second. And so in SI units, this is 38.4 meters per square second. So that's the acceleration of the collar relative to the rod at A. So finally, we need to solve for part C, and we want to find the transverse component or the theta component of the velocity of the collar at point B. So after the cord is cut, the only horizontal force acting on the collar is due to the spring, and thus angular momentum about the shaft is conserved. So using the conservation of angular momentum, we get the following. RA times the mass of the collar m times the transverse component of its velocity VA theta is equal to R at position B times m times its transverse component of velocity VB theta. And remember that the theta component of VA is equal to RA theta dot naught, the initial angular speed, theta dot. And so from here we can see that we can rearrange this and find the transverse component of the collar at point B. And this is, if we rearrange the equation, 150 millimeters over 450 millimeters. So RA over RB into 150 millimeters times theta dot, which is 16 radians per second, theta dot naught. And hence we get the transverse component of the collar at point B to be 800 millimeters per second. And this translates to 0.8 meters per second.